Hi, it's Mr. Anderson, and this is AP Physics Essentials, video 54. It's on angular momentum. Momentum, remember, is a product of the mass times the velocity of an object. So any object moving with mass has momentum. The only difference in angular momentum is it's rotating or spinning objects. And so if you were to try to get on this bicycle and balance without the kickstand out, you're probably going to fall over. But as you start to bike, as these wheels pick up angular momentum, they're going to resist changes, and it makes it easier for you to remain upright. And so angular momentum is a vector, and so there's a clear direction in which it acts. And in AP Physics, you should be able to understand the angular momentum of either a point object. So a point object is going to be an object accelerating around a point. So it could be, for example, an object attached to a spring or a planet orbiting around the sun. And the equation is very simple. L is equal to our angular momentum, again it's a vector, which is equal to r, that's going to be the radius from the center to the object, so that's the distance, times its linear momentum, which would be the mass times the velocity in a line. You also should be able to calculate the angular momentum of an extended object. So the whole object is rotating around a point. So to figure that out, all we say is that angular momentum is equal to I, where that's rotational inertia, times the angular velocity of the object. And again, that inertia is going to change depending on what that object is. Now, to figure out the direction of this vector, you'll use the right-hand rule. So if we look at this one right here, the object is spinning like that. So if you move your fingers in the direction of that spin, then we should have angular momentum that's moving in the upward direction. Whereas on this one, since it's rotating in the other direction, we're going to have it acting in the downward direction. Now, we learned when we were dealing with impulse that if you apply a force for a given period of time, that's going to equal the change in momentum of the object. Well, the same applies here. So the change in angular momentum is equal to not the impulse, but rather the torque times the change in time. So that net torque times the change in time is going to give us a change in that angular momentum. So angular momentum of this gyroscope, since we're spinning it in this plane, that's going to keep it spinning in that plane, and so it's able to resist changes due to gravity. There are really neat things we'll do in future videos, so you can take a wheel and give it a certain amount of angular momentum like that, and so it's conserved, but it can be transferred, some of that angular momentum, as we change the angle at which that force is actually acting. And so the two things you should be able to do in AP Physics is calculate the angular momentum of a point object. Again, that's an object that's moving or rotating around a given point. So this could be an object attached to a string, or the moon orbiting around the Earth. And so the formula is pretty easy. It's simply r, which is the radial distance here, times the linear momentum. So linear momentum is going to be in this direction, so it's the mass times the velocity. And so if you have these three bits of information, the velocity of the object, the mass, and the radius, all we do is simply multiply those together. So let's say we had an object, 1.1 kilogram mass, traveling at 3.2 meters per second, and then we've got about 28 centimeter here distance between the two. All we're going to do is multiply those values out, and then we're going to get an angular momentum of 0.99 kilogram meters squared per second. Now, the one thing I should have included here is that this is a vector value, so we have to add a direction to it. How do we figure out the direction? Well, since the rotation is like this, we use the right-hand rule to show that that angular momentum is going to be acting in the upward direction. You also should be able to calculate the angular momentum of an extended object, like this rotating cylinder here. All we do is multiply the rotational inertia times the angular velocity of that object. So if it's given, let's say we have an inertia of 15 kilogram meters squared, we multiply that times our angular velocity like that, and we're going to get 1.7 times 10 to the second kilogram meters squared per second. Now this again is a vector, and so what direction is that acting? Again, looking at my right hand rule, it's going to be acting in the upward direction. Now, how do we measure this in the physics lab? A good way to play around with this is using a turntable. So you can use a turntable that's attached to a desk. It has a certain amount of mass on it, and what you can do is you can give it a spin. So if we spin it in that direction, we try to make it as frictionless as we can. It's just going to keep spinning in that direction. And these are generally pretty heavy, so they have a large amount of rotational inertia. You can also attach a photo gate to it, so we can measure that angular velocity, or the speed at which it's turning in radians per second. And so you can do calculations of rotational inertia. We can also do collisions. Let's say we were to take another object. As the bottom object is spinning with a certain angular velocity, we could simply drop the top object on it. So what's going to happen is the angular momentum is going to be conserved, and so we're going to have to see a decrease when we put both of these together in its angular velocity. Also, you should understand how a change in torque or net torque over a given period of time is going to change the angular momentum. This is just like impulse in regular translational motion. And so here we've got an object and we're going to apply a force to it in this direction. Remember, if we apply a force perpendicular to the lever arm, we're going to get a torque. And so the torque is going to be in this direction. So I'm going to start the animation and watch what happens to the angular momentum. So as I add a force in that direction, we're getting an angular momentum in this direction. What's causing that angular momentum? Again, it's the lever arm now times the momentum in that direction. So as we apply a torque, it takes a while, but we're building up momentum in that direction. Now watch what happens if we change the torque in the other direction. So again, it's already has some movement or momentum in this direction, but now we've reversed the torque. So it's going to be applying a force in this direction, so the torque is down. Watch what happens. We're going to see a decrease in angular momentum, and then it goes in the other direction. And so again, as we apply a torque against that angular momentum, what do we get? At this point, we can bring it to a standstill like that. So how could we model this? Well, imagine we have this turntable right here, and I had rockets on either side, and they're going to apply a torque. So they're going to apply a force perpendicular to the lever arm, and as they do that over time, what's going to happen to the angular momentum? It's going to start to speed up in that direction. Now, how could you actually measure that without using rockets? You could use a setup like this. So we're using that turntable again. We could have a little bit of a wheel down on the bottom where we can apply a force to it. And so I'm having an object go off the table. Now we can apply a constant force in this direction. So that's going to be a torque over a given period of time. And that's going to give me my change in angular momentum. So did you learn to predict the behavior of objects in a collision as they conserve angular momentum? Could you calculate the angular momentum of both a point object and an extended object? And also, could you use torques and changing torques to see that how that impacts the angular momentum of the object? I hope so, and I hope that was helpful.